Hello and welcome to this video titled Network Topology Architectures. In this video we're going to cover several different types of network architectures. I'm going to introduce you to some concepts such as two-tier versus three-tier architectures. What is a spine leaf architecture? What type of WAN architectures exist? What about small office, home office architectures and on-premise versus cloud-based architectures? I'm going to introduce you to the differences in all these and what some of the characteristics are of each one of these. So let's start by answering the question, what is meant by a network architecture? What is that? Well, networks clearly, as you can probably guess by this point, can be designed in a variety of ways. Not only do you get to choose what devices you need for your networks, do I need a switch, do I need a router, do I need a wireless access point, do I need a controller, how many of these things do I need, but you also get to choose how these things are interconnected and where within your company or building are they going to be physically located. So all of those things will determine what type of network architecture you use. So depending on your positioning and placement of all these devices, it will dictate things such as what types of cables you need and where you need to place those cables and how long they need to be. Where will the data go? So when John's laptop is talking to the server that hosts all the files, what will the path of that data be? And if that path goes down, is there an alternate or redundant path that can be used? It'll also talk about redundancy. You know, all these different architectures, some have more or less redundancy than others. And in case you're not familiar with that term, what that's simply referring to is if a path in a network goes down, like a cable gets yanked out, someone accidentally spills coffee on a router switch and it short circuits, I want some alternative path available for my data to still reach its destination. That's redundancy. The more alternative paths you have, the more redundancy you have. Also, some of these architectures will dictate, do I need to use third-party services? In other words, can I make the architecture all on my own, all with my own cabling and my own networking devices, or do I need to contract the services from some outside provider to help me build some or most of the architecture I want to use? So let's start by looking at some of these architectures, starting with two-tier versus three-tier architectures. Now these architectures here, typically where you will find them is within your building. So we're talking about architectures here that are not for your house, but for your company. So a company's network, and these are typically mid to larger size companies that will implement these type of architectures I'm going to show you right here. So these are implemented in your local area network, in your LAN. Let's start with three-tier. Historically, three-tier first came out. This was the first design methodology for local area networks. And here's how it worked. The idea was that we're going to take our network and divide up into three different tiers. Each tier is going to have a different name and a different responsibility. So the lowest tier is what we call the access layer. These are the network devices that are giving my hosts, such as my laptops, my PCs, my servers, my tablets, physical connectivity to the network. So whatever the very first networking device is that my laptop, tablet, or PC touches, that device is at the access layer. Typically that's going to be one of two things. It's either going to be network-based switches or it's going to be wireless access points. That's what you would typically see at the access layer. So the primary job of the access layer is, like it sounds, to provide network access to whatever devices want to connect, and also possibly to implement authentication. Make sure that unauthorized devices are not allowed to connect and gain access to our network. Now after that, the next layer up is called the distribution layer. This would also be composed of either routers or switches that can do routing. The main idea here is that the access layer, we may have grouped together our hosts into different groups, such as maybe this group of hosts here is in the HR department. This guy over here is in marketing. And if HR wants to send data to this marketing server, the access layer devices might not know what that grouping looks like. They might not know how to get data from one group to the other, but the distribution layer will. So data that needs to go from one segment or one group of the network to another will pass through the distribution layer and then go back down again. So the distribution layer is in charge of routing. It might also be in charge of security. For example, if we say, okay, well, HR is allowed to go to marketing, but HR is not allowed to send data to payroll. Well, whatever networking security features we implement would be implemented at the distribution layer to contain that or control that. And then lastly, in the three-layer architecture, we have what's called the core layer. The idea behind the core layer is that this is a super, super fast layer that's meant just to get data from like major sections of our network to other major sections of our network. So for example, you might have two separate buildings. Each building has a bunch of access layer devices like switches and wireless access points. Each building has some stuff at the distribution layer. So in building A, any information that has to be routed or sent from corporate payroll to corporate marketing, both of which is in building A, would just stay in the distribution and access layer. It would just stay there. However, if anybody in building A needs to send data to another group that's in building B, now we send it all the way up to the core layer, and the core layer is responsible for super fast switching of data from one major section of the network, like a building, to another major section of the network, like another building. So the data should not be slowed down at all in the core layer. The idea here behind this three-layer or three-tier model is that there's going to be any delay in the data. If there's anything that's going to be slowing it down, it's going to happen right here at the distribution layer. Any routing or security features or anything that could potentially slow the data down where we have to look at the data, inspect the data, make a decision on the data would happen right there at the distribution layer. If data makes its way all the way up to the core layer, these things here are super, super fast networking devices. Their job is just to whip stuff across really quickly so that it can go down again. That's the core layer. Now this three-layer model, this is how Cisco recommended that networks be built for a long, long time. And this is because 20, 30 years ago, there were different devices. You actually had to buy a different type of device to do a core layer responsibility versus a distribution layer responsibility versus an access layer responsibility. You had to buy different devices to do this. Well, over time, more and more functionality has been built into devices to where these days customers say, you know what? I don't need to buy all this stuff to do the same types of things. The types of operations that are done at core, distribution, or access, I can actually shrink this down to less layers and accomplish the exact same thing. And that brings us over to the two-tier architecture. This is also sometimes called the collapsed core architecture. We don't really necessarily have a name for each layer at this point. I guess technically you could still say this could still be referred to as the access layer, possibly, because after all, it is giving access to the network, to our hosts. But the devices right here in layer 2, these are actually doing what this used to do. So my distribution and core layer are now being handled in just one tier instead of two. Hence, this is why they call it a two-tier architecture. Now, what are some of the characteristics, regardless of what hardware you buy or what software you use, what are some of the common characteristics of two-tier or three-tier architectures? Well, there's three things I could think of. Number one, this type of architecture allows for lots of different types of things at the access layer, because host devices have a variety of ways of connecting to the network. They might use wired Ethernet, in which case a network-based switch would be appropriate. They might use Wi-Fi, in which an access layer switch is appropriate. Hey, they might even use Bluetooth or something else, in which another device might be appropriate. So the access layer utilizes several different types of devices, or I should say could utilize several different types of devices in order to accommodate a wide variety of host devices. Okay, what else? What else is a common characteristic of this? Well, a lot of times you will find security implemented here. At the access layer, we might have security protocols that differentiate who's allowed onto the network and who's not. That would be a very big concern of these networks. So in your LANs, a lot of times authentication is done on your access layer devices. And also another characteristic of this is we want quick and easy connection to these devices. So we want to provide very common ports. We want to make the user's connection to the network very easy so they don't have to jump through a lot of hoops to get onto the network. So however that's done to make it easy and streamlined will be done at the access layer. All right, so this is for your campus or your enterprise network where your hosts are going to connect. Your laptops, your PCs, your wireless devices like your cell phone, your smartphones, and your tablets. But we also know that a network has another section where all of our file servers live. And this is what we call our data center. Our data center is where all our file servers live that have all of our mission critical data. So you can sort of think of your network within your company as subdivided into two main categories. You've got the campus or enterprise LAN, which is where all of your hosts live, and the network's used to get data back and forth to them. But most of the time, they're trying to access data in your servers. And your servers are all over here in a much more secure part of your network called the data center. Well, the architecture for a data center is not necessarily going to use this. A data center will use a different type of architecture, which we call a spine leaf architecture. So when you hear this term, spine leaf architecture, think data center. Okay, so in a spine leaf architecture, interconnections between switches can be layer 2 or layer 3. All right, so let's dig into this a little bit more. First of all, what makes this different than what we just saw? Well, number one, while of course our ultimate objective is that no part of the network should ever go down. We don't want any part of the network to ever go down. But if you think about it, if I'm dividing my network into the data center, which has my mission critical stuff, my data that's stored here, and everything else, if I have to decide between those two, my data center is much more valuable to me. That really can't ever go down. Yeah, I don't want this section over the network over here that's holding my hosts. I don't want that to go down either. But if I have to pick between the two, I'll spend the bigger bucks, get the better, faster, more resilient equipment, and put it over here in the data center. So one characteristic here of spine leaf is that these switches that you see, these aren't the same switches that your laptops and PCs are connecting to. Those are pretty pricey. These are super pricey. So the switches here in the spine leaf architecture are designed with the intent in mind of, number one, providing maximum resiliency and redundancy. These things are advertised as these will never go down. You buy one of these things, you can walk away, never have to worry about it going down. Of course, you're going to pay a premium for that because their power supplies are going to be super expensive to support that. They'll probably have multiple power supplies in case one goes down, another one can take up the job. So they'll have a whole bunch of resiliency and redundancy features built into them. So that's one thing that makes this architecture different. Another thing is that because this is where our mission critical data is, there's a lot of data coming to this spine leaf. There's a lot of hosts spread throughout our company, and all their requests, all their data is funneling into this. So these connections have to be super, super fast. So that's another difference, is in a spine leaf architecture, these interconnections between the switches and the connections leading down to the servers down below are typically going to be much faster connections than what you would find in the 2-tier or 3-tier, which is also going to drive up your price. The faster the connections, the more you pay for those types of ports and interfaces on routers and switches. So, and then lastly, notice multiple redundant connections here. Every switch on the bottom has a connection to every switch on the top. And the idea here is that this type of spine leaf architecture is best suited for what they call east-west traffic. In other words, traffic that's going like this, or going like this, or going like this. This is considered east-west traffic. The idea being that there's not going to be a lot of traffic going north-south. There will be some, but more of the traffic is going back and forth than up and down. So that's why we have all these redundant connections here between our spine switches. So these ones here are called our spine switches, and these here are called our leaf switches, hence where we get the term spine leaf. One other thing about this architecture I want you to be aware of, there's another term for this which is called the fabric. So if you ever hear somebody saying, oh yeah, my data center, my fabric is made up of blah, 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 blah. Well, the fabric, that means they're in a spine leaf architecture. And the fabric is all these switches, super fast, super redundant, super expensive switches, which are interconnected in the most redundant way possible. All right, so that's what you're going to find within your company. You're going to find a combination of these last three, 3-tier, 2-tier, and spine leaf architectures. Now chances are though, the data at some point is going to have to leave your company. You're going to want some data going out to the internet, or maybe going to a partner's organization that's across the street or across the city or in another different state or country. So for that, we need WAN networks. And just like there's different architectures that we can build within our company, like 2-tier, 3-tier, or spine leaf, there are different WAN architectures as well. So there's a variety of connection methods, and these basically break down into 3 different architectures. One architecture is point-to-point, which means that when you select this architecture, that means you've got, for example, an office maybe in Boston, and maybe another office in New York City. If you want a point-to-point WAN connection between those two, then that means that your telephone company or whoever sets up the point-to-point connection is going to set it up in such a way that when you put data on this wire right here, there's only one place it could possibly go, over to New York City. And when he puts data on his wire, there's only one place it could go, over to Boston. There's only 2 points at the end of this WAN, Boston, New York City. That's why they call it point-to-point. You say, well, Keith, what other options are there for me for WANs? Well, you see, the downside to this architecture is if I call it, so once again, let's say I had Boston here, and I had New York City here, and if I call up my WAN provider and say, hey, I want another point-to-point connection because I got another office coming online in Raleigh, North Carolina, and I want to connect that up. Okay, well, point-to-point means that's going to have to connect up to, for example, to here, to Boston, which means on Boston I'm going to have 2 physical cables coming in, terminating on 2 physical interfaces. That's going to require another interface on that router. My Boston router is going to have another available interface with another cable sticking out of it. And both these cables are going to terminate like in a wall jack or something at my office. Point to point. So more cables, more connections. Well, what other alternatives do we have? We also have what's called a broadcast-based WAN. For example, Metro Ethernet is like this. With Metro Ethernet, we have a situation where you connect to the WAN with some sort of a cable. Okay, it's most likely going to be a fiber optic cable. So this is a type of cable that's made out of like glass or plastic that's carrying light. So instead of carrying electrical energy to represent your data, light, like laser light, is going across that cable to represent your data. Now here's the big difference. In this one right here, once your data gets put onto the fiber ring, everybody connected to that ring will see it. So let's say, for example, that in this particular case, customer A was trying to send data to the ISP. Well, once customer A puts his data on there and starts going around this ring, broadcast-based WANs or even broadcast-based LANs mean that everybody connected to this network sees it. So that data will go to customer C. That data will also go to customer B, as well as going to the ISP. It'll even circle all around again, and it'll be the job of customer A to strip that data off the ring, to take it off of there. That's a broadcast-based WAN. Now you might look at that and say, wait a second, why would I ever want to use that? I mean, if I'm customer A, I don't want customer B and C to see my data. Well, here's the nice thing. In this type of a WAN, these switches that you see connected here, you don't actually own them. The ISP owns them. So all these switches are owned by the ISP. So whoever the building manager is of this building and this building and this building, they will go to the ISP and They'll say, hey, we want to connect to your broadcast-based WAN, your Metro Ethernet ring, for example. And so the ISP will walk in and put a switch in each one of these locations that connects up to this WAN. And then you, as the customer, you will actually be in charge of taking your own network equipment, like maybe you've got your own switch right here, and you'll connect it to this switch. Now I might say, well, how does that help me? Here's how it helps you. When your data goes right here and goes onto the WAN, yes, this switch will see it. So let's just put another switch right here. So this is actually owned by customer C. This switch right here is owned by customer B. This switch right here is owned by customer A. And here's what's the difference. Even though I'll just say right here, ISP, even though the ISP switch in this building sees the data, it will recognize, oh, this data is not actually meant for customer C. So that data will stop right here. So whoever, the actual customer who owns customer C switch won't see it. Only the ISP switch will see it. And same thing when it gets right here. Yes, this ISP switch will see it, but he'll say, hey, it's not meant for this building. So he'll sort of block it right there. So customer B switch won't see it. Once it gets over here, this ISP switch will say, oh yeah, that's for us. He'll pass it along through. But it's still called a broadcast-based WAN because every device that's physically connected to it is seeing everything. It just so happens that in most cases, the devices connected to this type of WAN are owned by a service provider. They're just placed in different buildings and sort of leased out or rented out to different customers. And then we have another type of a WAN called a non-broadcast multi-access WAN. This is a type of WAN where when you put your data onto it, you actually address your data in a certain way. And as that data enters the WAN, it will be kept separate from other people's data and then go across. So this is kind of like point-to-point in that if I had something like this in point-to-point, well, any data going across here was never going to be seen right here, right? This guy was never going to see that. Well, here's the difference. In point-to-point WANs, I had to select which interface I wanted. Did I want to put the data on this interface, which could only go over here, or do I want to put the data on this interface, which would go right here? Depending on which interface I selected, that's where the data went. In a non-broadcast multi-access WAN, I only have one physical connection to put my data on, but that data is addressed in a certain way that when it hits the WAN provider, and here's our WAN provider right here. When it hits the WAN provider, they have some super secret sauce to keep it separated so it will only go out to where it needs to go. My data will never be seen by any other customers because non-broadcast multi-access will prevent it. So it's called multi-access because, let's just look at this here for a second. So if this is the WAN here, this is probably a better picture. Let's say this is customer A. Let's say A has site 1, A has site 2, and A has site 3. And let's say connected to the same WAN is a totally different company. So it's got B1 and B2 connected. Well, when A1 sends the data, let's say he says, okay, I want this data to go over to my other site, A2. That's where I want this to be. So this data will have a certain address on it, like let's say 101. And these boxes here represent WAN switches owned by the service provider. Now, once it hits the WAN switch, that WAN switch will say, oh, 101, that means I need to switch it out like this way and send it to A2. So first of all, that data will never pop out here at A3 because that address didn't send it there. It'll certainly not pop out here to B2, and it won't pop out here to B1. The addressing will make sure it goes exactly where it needs to go. Now, this particular cable right here could be used by other customers as well, but you don't have to worry about that. Even though this cable is transporting data from multiple customers, the addresses in the data itself will keep the data separate and make sure it never pops out where it's not supposed to go. So the reason we call this multi-access is because this WAN cloud here that I've drawn, this thing right here, is a multi-access cloud. Lots of different devices can connect to it and use it to transport their data. A1 can use this one connection right here to send data to location A2 or location A3. It's not like point to point where A1 would need to have two cables. One cable going to A2, another cable going to A3. It's not like that. With multi-access, we've got one cable that we can use to reach multiple remote locations. But this is non-broadcast multi-access, meaning there is no way we could put data on this cable, one piece of data, and have it go out to A2 and A3 simultaneously. Can't do that. Because when the data puts on this cable, we have to give it some sort of an address. The WAN provider will tell you what that address is. And based on what address you put in that cable, in that data, it's going to go to one location or another. Maybe right behind this I put another piece of data on the exact same cable. Maybe the address for this one is 301. And when the WAN provider sees that, he knows, oh, okay, that needs to go to location A3. So this is non-broadcast multi-access. Another type of an architecture is a small office, home office. That's what SOHO stands for. Here you can see on the left you've got a small office. On the right you've got a home office. These are typically smaller networks, so we have less equipment demands, maybe just a single router or a single switch. And less need for authentication and security because you're in your house, you're in your small office, you designed all this. Very few people or devices are connecting to this. The downside of this is it's difficult to manage and enforce a policy from headquarters. In other words, if I'm at corporate headquarters, I'm the network admin, and I know that there's like 100 people that are working from home, so there's 100 home office networks out there connecting back to my corporate office, and there's like 3 or 4 small offices, like maybe branch offices that are connecting back to me. It's hard for me to say, okay, here's going to be our policy. Everybody has to use this kind of authentication, this type of security. Well, I can say that, but it's hard for me to enforce that because those 100 people that are working from home, what mechanism do I have to ensure that they've set up their little tiny network of like maybe one router and that's it with the policy that I've told them they should set up? Kind of difficult to enforce that. And the last two architectures I want to talk about are sort of supersets of the previous architectures we just looked at. On-premises versus cloud-based architecture. So an on-premise network, that just simply means that your network and all the devices, all the resources are right there at your building. It's on your premises. All the cables, all the switches, all the routers, all the servers, all the hosts, they're right there. So you can see everything, you can touch everything, you're in control of everything. Cloud-based network is a typical type of architecture where a company might say, you know what? What we need is like 25 different servers because we got 25 different kinds of data that people are needing to access in my company. Well, I could buy the 25 servers myself. Then I would be responsible for finding a place, a physical place in my building to put those things, making sure I've got enough air conditioning in that room so they don't overheat, determining the correct cabling to connect them out. Then I got to put the software on there. If they ever crash, I got to troubleshoot that and fix that. That would be on premises. That would all be my responsibility. Or I could say, you know what? There's a company out there called Amazon AWS, and they've got servers I can use. As long as I can get to the internet, I can rent servers from them. So why don't I take my 25 servers and put them in the cloud instead, have them reachable via the internet? Then I don't have to worry about the physical server. AWS, they figure that out. Amazon, they're responsible for if that server goes down, fixing it. They're responsible for patching it. They're responsible for figuring out how that server is going to be cabled to get back to the internet so I can get to it. That's a cloud-based network. So in a cloud-based network, the benefits of that are I could have multiple offices. Each office doesn't have to have their own set of servers. There's just one common set of servers in the internet hosted by a company like Amazon, and all my companies can get to those servers as long as they have internet connectivity. And it removes a lot of the responsibility from my shoulders and puts it on the shoulders of the cloud service provider. So that concludes this video on different network architectures. I hope you found it useful.